Okay, one is probably the one I understood the best. We are starting with the transfer function that it gives us, and it gives us these conditions. The process initially starts at 100 degrees Celsius. After 4 minutes and changing the input from 1 to 2 kilowatts, temperature is now 400 degrees Celsius, and 30 minutes later, it's 500 degrees Celsius. So given that P is the power input level and T is the temperature change, we can solve for P prime of T, which ends up being 1 kilowatt, and it's basically the change in P, and we can solve for T prime, which ends up being 400 degrees Celsius. And then from there, we can solve for K, which is just T prime divided by P prime, which is 400 over 1, which is just 400, but it's degrees Celsius per kilowatt. And then from there, we can look at T prime of T with this form, and we can plug in the second conditions it gave us in order to solve for tau, which ends up being 2.885 minutes. And part B is we're looking at if the change power input linear is, wow, that didn't make sense. We're changing the output linearly at 0.5 kilowatts per minute, and then we want to know when and how big the maximum rate of change of the process temperature. So we're looking at P prime of T. We can plug in the 0.5 kilowatts per minute into there, and then we renamed it to A just to make things easier for ourselves, and we can solve for K of A, which ends up being 200 degrees Celsius per minute because it's just the 400 times 0.5. And then from there, you can plug that back into T prime of T to solve for the new one. And so the max rate of change of the process temperature at T greater than or equal to 5 tau is greater than or equal to 5 tau. And it's also the 200 degrees Celsius per minute is equal to K of A. This occurs at 5 tau, which is 14.4 minutes. You graph the equation in order to figure that out, but this is only after transients have died out. Yay. Um, Number 6 was probably the one that I had the most trouble with talking about in class helped, but I still have questions. This is 520. I need to be able to look at it and not be confused. Okay. We're looking at tanks, ta-da, but we're looking at the component mass balance and the total mass balances. That's what we're starting with, and then you can um divide over this row over here so it looks a little bit better, and then we're linearizing and then taking the deviation variables the same step, and then we rearrange this all for C prime of S divided by C1 prime of S. And you plug that in, get that into a form that you can use Laplace-wise, and then just simplify it down so it looks more pretty than that. But then you can look at Cm prime of S over C prime of S, which is basic form that, and you can solve for K while looking at that. And since it's a change in output over the change in input, that just ends up being 1. And then tau equals t when Cvim of t equals 1.9. So that means that tau is 11 seconds. And if you can simplify that to minutes, which is 0.18 minutes. But then you can look at Cm of s and C1 prime of s, and solve for that, plug that in, and that ends up getting you the G of s. And then for part B, that's part A, but for part B, we're looking to find a response change for a step change in C from 14 to 17 pounds per feet cubed. And we can solve for Cm prime of t, which ends up being this lovely equation. In part C, if the transfer function was approximated by 1 unity, this one will be the step change. What sneeze? Okay, don't know. It's fine. Will be the step change for the system of the same input change, and that's basically solving for Cm of s in this way, and then transforming that back to Cm prime of t, which ends up getting you this. D is what I had trouble understanding. It's what can you say about the dynamics of the conductivity cell by comparing B and C? I get that they are virtually the same, so I don't really know what that means, though, when the dynamics are negligible. Um, yeah, thanks.